Welcome back everyone. From this lesson we are going to learn about another type of curve fitting which is known as the interpolation method. So in the last few lessons we learned about regression, that is another type of curve fitting purpose, and here we are going to learn about interpolation. So there are some basic differences between interpolation and regression. So if you remember from the last couple of lessons, if you know that in regression we are just fitting a line or a plane or a polynomial line through the data points. So that fitted curve need not go through all the data points in your space. So that means the line that you are fitting in regression, that line need not go through all the data points. Okay, but interpolation, in the interpolation method, that fitted line need to go through all of the data points in your space. So that's the difference between interpolation and regression. In interpolation, the fitted line goes through all the data points, but in regression the fitted line does not go through all the data points. So that is the difference. So first of all we are going to know about very basic type of interpolation, which is Newton's divided difference interpolating polynomial. So we are going to learn about this in the next few slides. So similar to the case of regression, the interpolating line that we are just fitting through the data points can be of any order. That can be of first order, that means a linear interpolating line, or a second order, or a quadratic interpolating line, or a third order or cubic interpolating line, or higher order. So we have just known this term higher order regression or linear regression, second order regression, polynomial regression in the last few lessons. So similar to the regression case, with the interpolating polynomials can be of any order: first order, second order, third order, or higher order. So look at this. In the first figure we are just fitting a simple straight line. That means we are just fitting a straight line through the two data points. So this is a first order interpolation. Similarly, we can fit a second order or quadratic line through three data points. Okay, for linear purpose we need two data points to fit a straight line. For quadratic purpose we need to have three data points to fit a quadratic line. And for higher order purpose, that means say we want to fit a third order or cubic polynomial, we need to have four data points, okay, to fit a third order cubic interpolating line. So that was the basics of interpolation: first order, second order, or third order. So what is the main summary here? If we are given n plus 1 data points, so we can fit a polynomial of order n. Okay, so if we are given just n plus 1 data points, we can fit one and only one polynomial of order n that passes all through the data points. So for example, in the first case we have just fitted a straight line. So to fit a straight line, it is a first order polynomial, we need to have two data points. Through two data points we can fit a straight line. Similarly, for through three data points we can fit a quadratic or second order polynomial. For four data points we can fit a third order polynomial. So that's the difference. The number of fitted polynomial, the order of the fitted polynomial is less than 1 than the number of data points. So this is the summary here, that for n plus 1 data points we can just fit in n order polynomial through all the data points. So first of all, let's look at the Newton's divided difference interpolating polynomial and the linear case. So this is the most popular and most useful form of interpolating methods in the practice. So for linear interpolating polynomial, since this is a linear interpolation, so that means we want to fit a straight line through the data points. First of all, to fit a straight line we need two data points. That means, let's see, in the example, in the figure, we are given two data points, x1 and x0. So corresponding to x0, the function value is f of x0. So this dot is the data point here, first data point, and the second data point is here at x1 where the function value is f of x1. So we need to fit a straight line through these 2 points. Okay, so that's the main purpose here. We need to fit a straight line. So for that purpose we are going to use the Newton divided difference interpolating polynomial. So let's see how this works. The simplest form of interpolation that connects these two lines that is denoted by this equation. So how this equation comes about? Let's look at the procedure. Let's say we are given a data point x that lies on between the x0 and x1, then the function value is between these two values, that means f of x0 and f of x1. That means f1 of x comma f1 of x, these data point lies on the straight line between the two given data points. Okay, so this is the approximation here. We are just assuming a data point, a third data point, x comma f1 of x, which lies on the straight line. So how this equation comes about? This is the linear interpolation equation, Newton's divided difference first order or linear interpolating polynomial equation. So how this equation comes? This equation can be derived easily from this figure. How? Let's say on the numerator in the left hand side we have this term f1 of x minus f of x naught. That means this height here, height of the smaller triangle, and the base of the smaller triangle is denoted by x minus x naught. Okay, so what does this term actually denote? This is actually the slope of the fitted straight line. So this is the slope of the fitted straight line, height divided by width or the base. Similarly, from the larger triangle here, which is formed by this x0, x1, f of x0 and f of x1, these two data points here, the larger triangle, we can similarly determine the same slope because the straight line is staying fixed. That means if we want to determine the slope from the larger triangle, it would give us the same value that is on the left hand side. That means we can get the same slope by the height of the larger triangle, which is f of x1 minus f of x0. That means this height, and the base is this, that means x1 minus x0. So we are just equating the slope of the straight line determined from two different points, so from two different triangles. So if we just algebraically manipulate this equation and determine the term f of x1, that means f1 of x, that means this is f1 of x. What does this term denote? f1 of x, x is denoted here, and f1 of x is the point that is situated on the straight line between these two points. That means f1 of x denotes any of the data points that lies on the straight line between these 2 points. Okay, so that is the main equation here, main purpose here. We need to find out the term f1 of x. So f1 of x can be easily determined from this equation, which is f of x naught plus this term. Okay, so that's the main interpolating polynomial, which is the linear interpolation formula of Newton's divided difference technique. But if you had noticed in the figure that the straight line do not actually capture the main features of the true curve. If you remember, the true curve was something like a curved parabolic curve, but we have just used a simple linear interpolation. That means using a straight line, we are just trying to find out the approximated value between the data points. But we can easily extend the first order polynomial, that means Newton's divided difference interpolating polynomial, up to higher order terms. That means the first order polynomial actually do not capture the main features of the data points nature. So we need to go for higher order interpolating polynomials. Let's say we want to use now quadratic interpolating polynomial. That means the order of the polynomial now is 2. So we can easily again determine the interpolating polynomials, Newton's divided difference interpolating polynomial of second order or quadratic equation, which can be denoted something like this, which is f2 of x equal to b naught plus b1 into x minus x naught plus b2 into x minus x naught into x minus x1. Since this is a quadratic interpolating polynomial, so we need to have at least three data points. Okay, we need to have at least 3 data points. So this is the general equation of a second order quadratic equation. So x naught, x1 and x are given, so we need to determine the f2 of x. So this is a second order interpolating polynomial. How this is a second order interpolating polynomial? We can easily verify that. We just multiply each of the terms here. So if we multiply those each of the terms, we can get this equation, and then we take the like order terms. That means for the constant terms are denoted as a naught, and the coefficients of the x terms are denoted by a1, and the coefficients of the x square are denoted by a2. So if we just notice here, a naught is denoted something like this, a1 is denoted something like this, and a2 is here. So this is the equation of a second order interpolating polynomial. So this is the fitted curve through the data points. So for fitting this curve, we need to have at least 2 data points. Okay, at least 3 data points. For fitting this, at least 3 data points. So now we need to determine the coefficient terms, that means the b0, b1 and b2 terms. So how we can get those terms? We can easily equate the quadratic equation at the given points. That means at x equal to x naught, we can easily input the value x naught into the fitted polynomial curve, that means the second order quadratic equation, and we can get this b naught equal to f of x naught. Similarly, we are just what we are doing here, we are just putting the x naught value into this equation. So if we just put x naught, this second term x minus x naught, this is going to be equal to 0. Similarly, the second term here x naught minus x naught, it is equal to be 0 here. So we are just left with b naught. So b naught equal to f of x naught. Okay, so we are just writing here. So b naught is nothing but the function value of the at the point x naught. Similarly, we can determine the other coefficients, that means b1 and b2. Let's say we at x equal to x1, what we are going to do here, at x equal to x1, this third term is going to be equal to 0, because x1 minus x1, this is going to be 0. So this third term is going to be equal to 0. So we are just left with b0 plus b1 times x1 minus x0. So b0 is already determined here, which is f of x0. So we can easily manipulate these 3 terms here and get the value of b1, which is f of x1 minus f of x0 divided by x1 minus x0. So b1 can be determined easily here. Last of all, we are just given we need to have the value of b2. So since we have already said this is a quadratic interpolating polynomial, we need to have 3 data points. So for x equal to x0, we have found the b0 coefficient. For the second data point x equal to x1, we have found the value of b1. Similarly, at the third data point, applying the third data point x equal to x2, we can get the value of b2. So b2 can be easily determined from these function. We just put the value of x equal to x2 here, and then we find the value of b2, which can be easily determined something like this. Okay, so all the coefficients are easily determined if we are given at least 3 data points for the purpose of fitting a quadratic interpolating polynomial. Okay, so we have just done some algebraic manipulations here to get the value of b2. So let's look at an example here so that we can easily apply the Newton's quadratic interpolation for the purpose of fitting this polynomial here. So we are just given 3 data points, x0 equal to 1, x1 equal to 4 and x2 equal to 6, and we are just given the corresponding 3 function values. So these are the 3 data points that we are given, and we need to fit a second order polynomial to these 3 points. So what is the main function that we want to fit, which is already determined in the, which is already mentioned in the couple of few slides before. If you remember, the general expression of a second order polynomial is b0 plus b1 into x minus x0 plus b2 into x minus x0 into x minus x1. So that was the main equation that we want to find out. But to get the equation, we need to find out the values of b0, b1 and b2. And we have already seen how we can determine these 3 values, these 3 coefficients from these 3 formulas. We have just determined these formulas from the in the previous slide. Okay. So all of these values, f of x0, f of x1, x1, x0, which is already given here in the question, so we can easily determine these 3 coefficients, b0 equal to 0, which is f of x0. Similarly, we can find out the value of b1 and we can get the value of b2. Okay, so once we get these 3 coefficient terms, we can easily substitute these 3 coefficients into the main equation of the second order polynomial, which is something like this: b0 plus b1, which is 0.462091, times x minus x0, which is 1, plus b2, which is here minus 0.051871, times x minus x0 times x minus x1. Okay, so this is the main second order interpolating polynomial. We can easily use this interpolating polynomial to find out the value of the function at any points between x equal to 1 and x equal to x0 and x equal to x2. Okay, so these quadratic interpolation polynomial can be used to find out the value of the function between the range of the x's given. Okay, we cannot apply this function to find out the value at a point that is beyond the range that is given in the question. Okay, so please remember that this interpolating polynomial is only applicable within that range, within 1 to 6. That means 1 to 6, this is the range that is given in the question here. So we cannot just apply this interpolating polynomial beyond this range. So for evaluating the function, so if we just say, for example, want to evaluate the function at x equal to 2, we can easily input the value x equal to 2 here, x equal to 2, and get the value of the function f of 2. So at x equal to 2, the function value is not given in the question, but using this interpolating polynomial, we can easily get the value of function at x equal to 2. So that's the main purpose of interpolation or regression. We are just finding out the value of the function at any point that is not given. Okay, so similarly we can just extend the order of the interpolation, Newton's interpolation, to up to n. So for nth order polynomial, so we need to have at least n plus 1 data points. Okay, for nth order polynomial we need to have at least n plus 1 data points. And if you just want to express the general equation of the nth order interpolation polynomial, which can be easily expressed something like this: b0 plus b1 times x minus x0 plus b2 times x minus x0 x minus x1 plus b3 times and dot dot dot. So we can easily extend the main general equation of the second order polynomial up to nth order interpolation polynomial. So as we said, for nth order polynomial we need to have n plus 1 data points. So these are the data points: x0, f of x0, this is the first data point; x1, f of x1, this is the second data point. Similarly up to the n plus 1th data point, which is xn, f of xn. So the equations can be easily determined, as we have seen in the case of second order polynomial. We can just substitute the values x0, f of x0 into the main equation, that means the general equation, and then we, by doing some algebraic manipulation, we can get all the coefficient terms, that means b0, b1, b2, b3 up to bn. So we have just seen these cases here for the case of second order polynomial, and we can just easily extend the same procedure for nth order polynomial. Okay, So in this way we can just determine here. So if you just remember the finite divided differences lesson, which is covered in lesson 4 of this course, you just determined how you can apply the divided difference equation to find out the value of the differentiation. So if you just see that these Newton interpolation polynomial are nothing but just the finite divided difference formulas. Okay, so they are just same actually. So if you remember from the lesson 4 that f of xi and xj, which can be easily determined by f of xi minus f of xj divided by xi minus xj. So what we are doing here, now for the purpose of nth order interpolation polynomial, we need to determine the coefficients b0, b1, b2, b3, something like those. So we can get a general expression here. So we need to find out these values, f of xi xj, f of xi xj xk. So these terms are easily determined through these formulas. For example, if you want to find out f of xi xj, that are always determined with these formula. That means if you are given two data points xi xj, you can find out these value f of xi xj by this formula. Similarly, through three data points you can determine the value through this equation. But look at this, in these three data points f of xi xj xk, in the numerator we need to find these value f of xi xj and f of xj xk, which can be easily determined using these second order functional values. Okay, so this is actually a succeeding formulas. We just first determine these terms, and then we just using these two terms, using these two variable terms, we can determine the three variable terms. Similarly, using three variable terms, we can easily determine the fourth variable terms, and then we can just easily go on to up to nth variable terms. Okay, so this is the general equation here. So we can just easily implement these Newton interpolation formula into the MATLAB code as a loop, and we can find out the value of the nth order interpolating polynomial coefficients. Okay, so let's look at the chart that will help you to find out how an nth order interpolating polynomial helps you to find out the coefficients. For example, we are given four data points here, 0, 1, 2, 3, and the corresponding x points are x0, x1, x2 and x3, and the corresponding functional values are these. So taking just two function values, say for example f of x0, f of x1, and the corresponding x0 and x1, we can just easily determine the second two variable functional values here. That means f of x1, f of x0. So which can be easily determined by this formula. Okay, which is f of xi minus f of xj divided by xi minus xj. So f of x0, f of x1 comma x0, which can be easily determined by f of x1 minus f of x0 divided by x1 minus x0. Similarly, by taking other two variables, let's say x1 and x2 and the corresponding function values, we can easily determine these second two variable function value, that means f of x2, x1. Similarly, using f of x2 and f of x3 with the help of x2 and x3, we can determine this second order function value. Now in the third case, we can easily determine the second column, which is denoted as the three variable function values. So for determining these three variable function values, we need to use these first two variable function values. So using these two variable function values, we can determine these three variable function values. Similarly, using these two variable function values, we can get the second three variable function values. And lastly, in the third case, we can determine this four variable function value using these two three variable function values. So that is actually a succeeding approach. Okay, in the succeeding cases, you just use the previously determined values to determine the function values here. Okay, once you determine these function values, you can easily get the coefficients that you have seen in the previous slide. Okay, so let's look at an example here. So we can easily implement an nth order interpolating polynomial into the data points. For example, let's say we have four data points given, which is x0, x1, x2 and x3, and also we are given the corresponding function values here, f of x0, f of x1, f of x2, and f of x3. So what we are going to do, we need to fit a third order Newton's interpolating polynomial to these data points. Okay, third order Newton's interpolating polynomial. So we are going to use the chart that we have just seen. So let's see how we can do that. So since we are going to implement a third order interpolating polynomial, so we need to have 4 data points. So we are already given the 4 data points. So the general expression for the third order polynomial can be easily written something like this. So we have already seen how the second order interpolating polynomial was written up to this term, up to the third term. For the third order interpolating polynomial, we need to express the equation up to the fourth term. Okay, so what we are given here, we are given just the x0, x1, x2 variables here and the corresponding function values, and we need to determine these coefficients b0, b1, b2 and b3. So that's the main purpose. We need to find out these coefficient terms b0, b1, b2 and b3. So once we determine these 4 coefficient terms, we can easily substitute those coefficient terms into this formula and we can just get the third order polynomial. Okay, so how we are going to do that, let's see. So we need to find out the coefficients, and if you remember from the couple of slides before that b0 is denoted as f of x0, b1 is denoted as f of x1 comma x0, b2 is denoted as f of x2, x1, x0. Similarly up to bn we can easily determine the function values. Okay, so let's see how we can do that. We have already seen how to calculate these function values, 2 variable function value, 3 variable function value from the previous slide. So we have seen that in the chart. So we are going to apply the same chart here. Okay, so this chart that was given in the previous slide, so we are going to apply this. First of all, we need to determine this column here, that means the 2 variable function values. So how we can do that? So f of x1, x0, that means these function value which can be easily determined by using these 2 variables, that means f of x1 minus f of x0 divided by x1 minus x0. Okay, so x0, x1, x2, x3, these are the values that are already given in the question. So we can easily determine f of x1 and x0. Similarly, for the determining the f of x2 comma x1, we need to use these 2 rows, that means f of x1, f of x2, x1 and x2. That means these 2 rows, that these 2 function values and the corresponding x values can be used to determine this f of x2 comma x1. That means f of x2 comma x1 is equal to f of x2 minus f of x1 divided by x2 minus x1. Similarly, f of x3 comma x2 is equal to f of x3 minus f of x2 divided by x3 minus x2. So this way we can easily determine the second variable, that means the 2 variable function values. Next, we need to determine this column with where we have the 3 variable function values, which can be easily determined using this formula. So to determine the f of x2, x1, x0, we have to use these 2 variables, that means f of x1 comma f of x0 divided and f of x2 comma f of x2 comma x1. So these 2 terms can be used to determine the value of the second variable or the 3 variable function values. Okay, so look at these variable, these 2 terms here, f of x1 comma x0 and f of x2 comma x1. So these 2 terms has x values which are in the range of x0, x1, x2. That means they are within this range. Okay, so in the denominator we need to use the difference between the largest and the smallest x variable. That means since we need to determine f of x2, x1, x0, and we need to use these 2 second variable function values, these 2 second variable function values range up to x2, from x0 to x2. That's why in the denominator we need to use the difference between x2 and x0. Okay, that is 6 minus 1. Similarly, for the second case, the third order second variable, which is the f of x3 comma x2 comma x1. Okay, we need to use these two variables here. That means from this column we need to use these two variables, f of x2 comma x1 and f of x3 comma x2. These two function values range within the range of x1 and x3. So in the denominator we need to use the difference between x3 and x1, which is 5 minus 4. Okay, so that's how we determine this column. Similarly, lastly, for the third case, we can easily determine the value of f of x3, x2, x1, x0 using the values that was determined previously, f of x2, x1, x0 and f of x3, x2, x1, and these two function values range within the range of x0 and x3, and that's why in the denominator we are just using the difference between the largest and the smallest, which are x3 minus x0. That means 5 minus 1. Okay, so once we determine these three columns, we have already determined all the terms here, f of x1 x0, f of x2 x1 x0 and f of x3 x2 x1 x0. So we can easily equate these values to b0, b1, b2, b3, etc. So once we determine these coefficients, which are b0, b1, b2, b3, we can easily substitute these terms. b0 is actually equal to f of x0, b1 is actually equal to f of x1 x0, b2 is actually equal to f of x2 x1 x0. So these are actually all the first terms in each columns. Okay, these function values, these are actually the first terms in each column. So these are actually the coefficients. Okay, so these coefficients, once we determine these coefficients, we can easily substitute those into the main equation, the general third order interpolating polynomial, and we can get this interpolating polynomial, which looks like this. So this is the this is our main interpolating polynomial that we wanted to fit. This is a third order interpolating polynomial. So why this is a third order interpolating polynomial? If you just multiply all of these terms, you can see that the highest order x terms is actually 3. So that makes the third order interpolating polynomial, and this is the Newton's third order interpolation polynomial. So that makes the end of this lesson. We have just learned about how we can use the Newton divided difference interpolating polynomial for the linear case or the quadratic case or the third order cubic case. So we have already seen an example, and we have seen how to how to find out the coefficients of the interpolating polynomials using those charts, and we have seen how to use the 2 variable function values, 3 variable function values, so we can easily determine the coefficients. So that makes the end of this lesson. So please try out the MATLAB code that I have attached with the Newton's interpolating polynomial along with this video. In the next lesson, we are going to learn about another interpolation technique, which is known as the Lagrange interpolating polynomial. So in this lesson, we have learned about Newton's interpolating polynomial. Now we are going to learn about another interpolating polynomial, Lagrange interpolation polynomial. So till then, thank you so much.